This semester's big question is, why do visionary leaders adapt? And the answer to that question is visionary leaders adapt with transformation so that they can move on to the next step. Without adapting, they cannot match the pace with society, hence leading in an unbalanced rate. Moving on to the focus question for this project, the question stated how can human analyze transformation based on physics concept and law in a day-to-day life activities. The right answer to the question would be human can analyze the concept by realizing an unbalanced force. With the realization, they would be able to analyze the motion that can make energy. In this project, there is two outcomes that is going to be covered. The first one being the third outcome of the physics course, able to develop a forward-thinking design based on the understanding of Newton's law of motion. And the second one is the fourth outcome, which is able to analyze a daily life problem based on the principle of work, energy, and power. Starting with the free body diagram, it can be seen in the picture that there is a child putting her hand on her face. The hand indicates an object where the face indicates the surface. From here, the normal force can be drawn. From the picture, the force can be placed in the hand where it pulls the skin. The force itself is not balanced. The hand slides down the face, creating friction force to the opposite direction. Gravity too plays a role to why the hand moves, which means gravity plays a role in the diagram as well. This is the finalized free body diagram. Moving on to Newton's first law of motion, it stated that every object will remain at rest or in uniform options in straight lines unless acted upon an unbalanced force, also known as the law of inertia. In the picture shows a little girl standing still. This picture can be analyzed because it shows inertia. With the girl standing, it shows a normal force upwards and gravity pulling it downwards. This picture can be concluded as inertia. In Newton's second law, it stated that force is equals to mass times acceleration. This means that a change in mass will affect the acceleration created and the force needed. The picture shows a little girl riding a robotic cow. From here, it can be analyzed that the normal force is located between the object and the surface facing upwards, while the weight facing downwards alongside gravity that plays a role. The force too was created by a figure behind the girl. Because the weight in the previous picture is different from the current picture, the amount of force needed will be different. The next law will be Newton's third law of motion, where it stated that for every action there is always an equal force on the opposite direction, also known as law of action-reaction. In the picture shows Sung Kwan playing volleyball. From here we can analyze the picture by placing normal force with the ball and the hand. Then the force used to push the ball forward, and for the ball to come back, gravity plays its role. Because the ball bounces back, the hand creates a force to the opposite direction, pushing the fingers backwards. This shows the law of action-reaction. Moving on to the next topic, which is conservation of energy. The picture shows Jun, one of 17th Chinese member, going down the slide. There he is located in point A. But what is the potential energy and the kinetic energy of this action? From the picture, it was given that the height of the slide is 2 meters and Jun's mass equals to 66 kilograms. The calculation can proceed with firstly finding the potential energy. Potential energy has a formula of mass times height times acceleration of gravity. From here, we can put our given information in the formula, making potential energy equals to 66 times 2 times 10. The equation then results to 1320 joules. Next, we will move on to finding the kinetic energy, where the formula is kinetic energy equals to 1 per 2 times mass times velocity square. We can then put the given information resulting to 1 per 2 times 66. Because Jun is at its peak of energy, we will give the velocity a 0. We then calculate it to have the final answer, which is 0. Moving on to the mechanical energy, it has the formula of potential energy plus kinetic energy. We can put the information from our previous calculation, making 1320 joules plus 0, which equals to 1320 joules. However, to prove conservation of energy, we need to see Jun creating kinetic energy. To find it, we can calculate Jun's potential energy and kinetic energy at point B. From the given information and the previous calculations, we can conclude that the height of the slide at point B is 0, while June's mass is 66 kilograms, the acceleration of gravity is 10 meters per second square, and the potential energy of point A is 1320 joules, while the kinetic energy of point A is 0. To find the kinetic energy of point B, we need to find the potential energy of point B first. Using the same formula, we can put the given information, making an equation of potential energy equals to 66 times 0 times 10, where the result shows 0 as the answer. We now know the potential energy. We can find the kinetic energy through the formula of mechanical energy, which is potential energy A plus kinetic energy A equals to potential energy B plus kinetic energy B. Putting the given information, we can leave the kinetic energy B as KE. After the calculations, the kinetic energy of point B shows a result of 1320 joules. From here, we are able to find velocity using the formula of kinetic energy. We input the given information, then calculating it, showing the result of 6.3 meters per second. From the calculations, it can be concluded that the mechanical energy of point A is equal to the mechanical energy of point B. With the results, it can be proven that the picture shows conservation of energy.